right, Honor Chem students, this is part 2 of today's learning on how we calculate enthalpy, or what we call heat content. So first of all, you'll notice here that I've got a picture of a methane molecule and an oxygen molecule, and when they react, they will make CO2 plus water. This isn't a balanced chemical equation by any means, but I wanted to show you guys the structure, and this again is just a model of what we think the structure of methane looks like, that there's a chemical bond here. There's a bond in between two oxygen atoms because we know it's a diatomic molecule. Well, in a chemical reaction, you guys have heard this, is that, matter is not created or destroyed, it's just simply rearranged. And what you notice here is that these bonds have to be broken. The carbon-hydrogen bonds are broken, the oxygen-oxygen bonds are broken, and then they're rearranged to make CO2 plus water, so new bonds are formed. If there's energy left over after this formation, the reaction is going to end up being exothermic. If it requires more energy to make this reaction than what this can happen, the reaction is going to be endothermic. And there's going to be a convenient way that we can calculate this energy, which we call enthalpy, or what we call change in enthalpy. That's what the delta means. By this reaction, or this equation, the sum of the products minus the sum of the reactants. So just to recap, enthalpy, remember, means energy or heat constant. So potential energy is stored in the bonds of the molecules. That's what I'm talking about here. And when we are at constant pressure, which is most of the time, most of our chemical reactions that we do, we don't have changing pressure. We're doing it at room pressure. That pressure stays constant then. And we cannot measure heat alone. We can only measure a change in heat. Okay, so that's kind of back to those enthalpy diagrams that you can only see, like if it's, here's, reactant, or if it's, the reactants or products, and I'm getting a little weird here with just the difference on the two types would represent the delta H. That difference represents the delta H either being endothermic or exothermic. So this is the equation of importance, the sum of the products minus the sum of the reactants. And we actually will show that symbolically a little differently as well, where we can say here the delta H. So you might see me representing it this way, the delta H, and you'll see this big sigma here. That sigma means summation. And you do have to incorporate moles. So as I'm doing that, you'll notice that this N stands for the moles that are in the reaction. So we call that the sum of the products minus the sum of the reactants, and you have to consider the moles. Now, because this is energy, the units are going to be in joules or kilojoules or calories or kilocalories. So what do you have to use here to be able to calculate the sum of the product minus the sum of the reactant? Well, you're going to use, this is page 1 of your enthalpy table from the thermodynamic data that you either printed or you downloaded from the first day that we were doing energy. And here you also will notice that pure substances are not on this table here. They're only compounds, and you'll notice there's states of compounds, and the states of the matter will matter, so you have to pay attention to that. But pure compounds like pure oxygen, pure copper, pure aluminum, pure iron, pure hydrogen, any of the diatomics like chlorine and fluorine and iodine, even though they're diatomic, they all will have a delta H of 0 kilojoules per mole. Okay, so if it's a pure compound, it's not on your front page, but just know that it's a 0. Okay, so what I want you guys to do now, and you can pause the video if you have to, you need to go find the worksheet, and it's usually attached to the bottom of this lesson, and we're going to do the first problem together. So I want you guys to go and get that piece. You can either open it up in a new screen, if you print them out, whatever you need to do, but you can hit pause, go find that worksheet. Okay, so hopefully you found your worksheet, and like I said, it's at the bottom of the lesson page, and you're going to see that it looks like this. It says enthalpy is the worksheet, and it says given the balanced equation, find the change in enthalpy, which means the delta H. And for some reason, when we're printing things, the delta sign doesn't come out. So if you see DH, you should know that that means delta H, okay? And hopefully your version as well has an arrow here. For some reason, it's not showing up here. So, oops, I'm trying to draw my arrow and I'm getting all mixed up now. So here, we're going to see if we can fix this. Just give me a second. So there should be an arrow between the oxygen and the water molecule. So I'm going to give it my try here again to do an arrow. And for some reason it's not working. There we go. So there's an arrow there between the water and the oxygen, okay? And you'll notice I got the answer there for you, but you're going to have to show your work on how you get this work. And then I'm wondering if this overall reaction is endothermic and exothermic. So when you do this, we're going to go back to here. Remember, we're using this equation, the sum of the products minus the sum of the reactants. So, and we're going to have to use the data here, okay? So I have this printed out on my sheet, and I also have it as a standalone picture on the learning page. But this is the equation. So you're going to do this delta H is equal to, now notice I'm looking at gaseous water, and I have 2 moles of it here. Right here I have 2 moles. So I'm going to type in or write down 2 moles, and then I use the parenthesis signs, and I found the delta H per mole for gaseous water. Where did I find that? I looked at this sheet right here, and hopefully right here, gaseous water is negative 241.8. And since I have 2 moles in the balanced equation, that's why I have a 2 mole here. So the sum of the products minus the sum of the reactants. Here's the first reactant. The second reactant is SO2. I do the same thing. I've used my 2 moles. I found this value for gaseous SO2 on that sheet. Okay. Then you'll notice that I have minus, I put these all in a bracket. Then I go minus 2 moles. So that's this right here for H2S. I looked that up on the sheet. It's negative 20.5 kilojoules per mole. And then you will notice I have 3 moles times 0. Now, oxygen wasn't on that sheet, but I know that oxygen is a oxygen is a pure substance. So therefore it's 0 kilojoules per mole. Now, I strongly suggest you guys write this all out and then you solve what's in the brackets. So here I got a negative 10.77.2 kilojoules, and here 3 times 0 is 0. So it's really just going to be 2 times 20.5, which gave me the 41. And now I solve for the delta H. And remember, when you're, this is a negative times another negative will make it a positive. So that's why you subtract basically negative 1077, and then you're adding a positive 41 kilojoules. So this is what I got for my overall answer, negative 1036.2 kilojoules. Now, because this is negative, the delta H is negative, hopefully you know from the first lesson, that means the reaction's exothermic. See? Pretty simple. Now, I strongly suggest, as I'll just say it again, you guys should definitely write this out and take care when you're doing your math. Sometimes kids get the wrong answer because they don't do products minus reactants. So I'm just letting you know that that is a really common issue that kids run into as part of their problem with the worksheet. So that is how you do one of these enthalpies. I strongly suggest that you do the worksheet because, as you know, the homework test or the homework and the test, which will be some multiple choice questions on math, will be like this homework. All right? And again, just contact me if you have any questions. Have a good day.